Hi, and a very nice welcome to the first part of our webinar series of Simple and Accurate with Allplan Bridge. My name is Jan Ostersch, and I'm a technical consultant at the Allplan Infrastructure Competence Center in Graz. And today, we are going to talk about the modeling of precast girder bridges. But before we are going deeper into the new workflow we have built into the product, I will make a short introduction for all of you who might have never seen or heard about Allplan Bridge. I will very quickly present what the Allplan Bridge solution is and cover the initial modeling approach released with the first version only 3.5 years ago. In the next step, I will briefly explain the theory behind the new modeling approach, but the heart and soul of today's webinar will be the live demonstration, which will show the workflow as simple and accurate as promised. The Allplan Bridge solution consists of 3 applications linked between each other. It allows you to use one solution and only one bridge model for the complete beam-supported bridge design workflow. From parametric modeling to drawing production, including structural analysis and reinforcement design. This not only shortens the design process, but also improves it, especially because there is no data loss and there is no redundant data input. And because Allplan strongly supports also the open BIM approach, the data can be shared with the outside world at any time, and the final deliverables can be handed over in any format. The solution consists of Allplan Bridge. Here we can generate an exact 4-dimensional geometrical model from which the analytical model can be derived and used for structural analysis and reinforcement design. The very same geometrical model can be used in Allplan Engineering for detailing and drawing production, and also in Allplan BIM Plus, which is the ultimate collaboration and exchange platform. In Allplan Bridge, more or less everything starts with an axis. The axis can be either defined directly or it can be imported as a length XML format. In the next step, the typical cross-sections are defined. Here the user has no limits, because an arbitrary cross-section geometry can be defined and each parameter in the section can be set as a variable, and for it any variation can be set. In the final step, everything is merged into the 3D geometry by extruding the section along the axis. According to the designed relations in the cross-section and the defined variation, the product calculates the final 3D geometry. In the same manner, all bridge elements can be modeled: main girders, piers, transversal elements, foundations, and so on. And once the main structure is defined, we can model any type of pre-stressing tendons. We can assign any material to the bridge elements and even introduce the 4th dimension, time, of course, by specifying the construction sequence. This advanced modeling approach is especially tailored for bridges with a geometry that is directly governed by the axis. However, as a lot of you know, there are many bridges of different types and shapes built in different ways. And some of their geometries are only indirectly governed by the geometry of the axis, like Precast Girder bridges. And all of this we have considered when designing the new version of Allplan Bridge. All the new features result in a new workflow, and in combination with the existing modeling approach, any geometry of a prefabricated girder bridge can be modeled with ease. Like the original modeling approach, first the axis needs to be generated or imported, and then the geometry of the section can be designed or used from a template. Once this is set, first the substructure with or without foundation must be generated. In a subsequent step, like on the construction side, the prefabricated girders are positioned on it. For modeling of the deck, the original approach can be used: extrusion of a cross-section along the axis. And at this point, we have generated 2 bridge elements with 2 different approaches, and hereby a gap is generated. We all know it by the name of a haunch or fillet, and its 3D geometry is highly arbitrary. In Allplan Bridge, we have found a very simple solution for the modeling of the haunch, and for this we use the 3D Boolean operations. This concludes the modeling, and the model can be finalized. But of course, several new functionalities and modeling elements were introduced to support this workflow. However, the main difference is the adjusted calculation procedure, which supports the new modeling method. But let's go now a bit deeper In the next few slides, I will present all the steps of this new modeling workflow in a little more detail. But we will see then a bit later on in the live demonstration how all this works together in the software. For easy but precise modeling of precast girders, we have implemented a new element, which is called a link girder. Same as for precast girders in the physical world, a link girder is a straight element. In one simple description, we could say that the link girder is a linear, or let's say straight, 3D element between two 3D points. These two 3D reference points, or geometric positions, define the virtual and local axis which is used for the calculation of their geometry. From here on, the standard modeling approach is applicable, including their variation. Once the geometry of a girder is set, it can be finalized as usual. We can use it for tendon modeling, construction sequence definition, and later on in Allplan engineering for detailing, rebar modeling, and drawing production. Last, but certainly not least, a link girder is a parametric element allowing you to implement changes easily and quickly. A further characteristic aspect that is common for prefabricated girder bridges is the repetition of the shape and length of the girder. Depending on the global bridge constraints, like for example radius of the axis, identical girders are positioned either in the same span or at the same position span-wise. Here, there are no limits, and despite the fact that often for girders standardized shapes are used repeatedly, each bridge is still unique. The new modeling approach is open and therefore supports also this aspect. And to support also the repetition of the girder geometry, we are introducing modular modeling. Here, you can generate as many templates as necessary, either for link girder elements to model the prefabricated girders, or for pier elements to model the substructure. The virtual axis is straight and is horizontal or vertical depending on the element. And from here on, again, the initial modeling approach can be used to generate any shape of any variation. Once the template is generated, it can be used by simple drag and drop in the main 3D model as many times as necessary. And hereby the length can be automatically adjusted, or it can be taken directly from the template. What exactly I mean with that, I will explain in a second, but the fact is that by using this approach, a lot of time is saved. I forgot to point out one important aspect, and this is that both the template itself and the target element in the final model are, as all elements in Allplan Bridge, parametric. Combining all the new features together, changes can be introduced not only at one place and are adjusted through the complete 3D model automatically. Imagine you're almost done with the modeling and you need to adjust the girder geometry. Having 50 girders, that would become a time-consuming task. But if all girders reference to one template, the change needs to be incorporated only in one place. Okay, let's now have a look at what is the new workflow resulting from the new element type, link girder, and the modular modeling approach. First, the template needs to be generated. In case of link girders, the axis in this virtual space is straight and horizontal. Using the well-known workflow, the section is assigned and the variation is introduced. In the next step, the template can be used and the link girder is positioned on the substructure by clicking the first and second reference point. Both are generated while modeling the substructure geometry. Once the points are selected, the begin and end axis length can be set directly in the modeling process or later in the property grid. Once the geometry is final, we can add all the details like tendon geometry using the standard approach. To generate all other girders, we can use the same approach that was shown just now, or we can simply copy this girder as many times as necessary. In this way, all girders can be generated very quickly, and I think now you can see why this approach will not only save time, but will also generate an exact geometry. And the length of the girder is of course the key point when talking about an exact geometry. Especially when the section of the girder varies along the girder length and when for modeling templates are being used. Why? Because we do not know the exact length of the girder when modeling the template. The technology we have implemented allows both, either that the length of the template is same as the girder length, or that the length of the template is virtual and that the girder length is specified when positioning it on the substructure. In this case, we could say that the girder length is adjusted, or let's say stretched. Which approach to use strongly depends on the bridge geometry and which one is more convenient. In both cases, the distance between the reference points, so in this, let's call them GP1, GP2, which stands for geometric points, is given. It is set by the geometry of the substructure. In case the length of the template represents also the length of the final girder, the begin and end axis length results from the difference between the template length and the distance between the reference points GP1 and GP2. In the second option, the length of the template does not play an important role, as the final length of the girder is given by the distance between the reference points and the defined begin and end axis length. But what happens if the girder geometry varies along its length? Let's take a look at that. To solve this as conveniently as possible, we have introduced new types of stations. In this case, where the position of the station does not influence the final girder geometry, you can use a simple station as until now. This will stretch in the same relation as the girder length. In the case when position of the cross-section change is fixed, you can now use the new station types. Let's call them fixed stations. And with the help of these, it is possible to fix the station that governs the girder geometry. Below we can see a perfect example. At the begin and end of the girder, we have two fixed positions that govern the girder geometry, regardless of the girder length. They are always at the same position. Let's say always 1 and 3 meters from begin and end of the girder. This can be fixed with this new station type, and all other stations between them can be set as free or variable, as they do not govern the girder geometry. Using this, we can still adjust or scale the final girder length, and the fixed stations will remain on their defined positions. This can also be seen in the picture below. In this case, the same template is used, but as the stations are fixed, the begin and end of girders remains unchanged, despite that the girder length was stretched. This also strongly shortens the time invested for modeling of these types of girders. Once all the girders are modeled, the next bridge element that can and must be generated is the bridge deck. Normally, the plate is cast on site, and as it represents the base for the roadway, its geometry is governed by the axis. Thus, the standard modeling approach can be used. Next, and almost the last step, which might also be the trickiest, is closing, or let's say filling the gap between the girders and the plate. By this I mean modeling of the haunch. There are many constraints that govern the 3D geometry of the haunch in order to provide geometric and physical unity between the deck and the girders. The basic geometry is given by the shape of the haunch itself. We could also say by its cross-section. On the cross-section level, also the cross-slope of the slab and the girder arrangement determines its geometry, especially because the girder's top flanges are horizontal. In the longitudinal direction, the geometrical inconsistency between the plate and the girders characterizes the haunch geometry. The slab follows the axis, and with this the elevation of the road, where on the other side the girders are straight. This results in a variable haunch thickness. Furthermore, also the construction process and the vertical deflections of girders dictate the final shape of the haunch. As just illustrated, the final 3D-dimensional form of the haunch can be quite complex. However, we can also read out that the haunch geometry is more or less governed by the surroundings. And this fact we can use to our advantage. In Allplan Bridge, you just need to define the geometry of the haunch on the cross-section level. This is in the cross-section definition window. And the final 3D-dimensional haunch form is automatically calculated and generated using 3D booleans. This is possible because all parameters which govern its geometry are already defined. Practically, the haunch just needs to be predefined in such a way that it intersects the plate, and so it can be merged using the unity function together with the plate. With the finished haunch definition, the modeling of the main bridge elements is done. Now all other details like diaphragms, bearings, side curbs, parapets, pavements, barriers, and so on can be modeled using the initial modeling approach. New types of elements or by placing Python parts. With this, I would like to conclude my theoretical part of the presentation. I hope you can see how all that new features result in a new modeling approach, which is especially tailored for the prefabricated girder bridges. The straightforward definition speeds up the modeling process and allows you to generate an exact model with ease. But now I would like to invite you that we go directly into the software and do the live demonstration. But before we do this, I would just like to show you what kind of bridge we are going to create in the next 20 or 25 minutes. So let's go directly into the software. As you can see, I'm already in my software. And you can see that I have already something prepared. For those of you who know Allplan Bridge already, this will be a familiar interface. So maybe I will just show you quickly what I have already prepared. So in the 3D modeling window, you see two axes. One in a red color, this represents the road axis, and then we have one in the yellow color, which represents the terrain axis. And this is also a new addition to this version, which is called accompanying axis. And what does this mean? This means that these two axes are parametrically bound to each other. So let me demonstrate this. I can create a road axis with a certain profile, and then I can create a terrain axis with a certain other profile, which we can see from the side. But the parametricity here is that if I move the road axis, for example, if I change the radius to, let's say, 300, also the terrain axis moves with it. So, okay. What I have also prepared, I've prepared a few cross sections that we're going to use, and maybe show you this one. So for the main girder. This is a prefabricated concrete eye girder, where I have already prepared this empty boundary that will serve for the Haunch definition, so for the Haunch geometry. We will see how this is applicable later. What I have also prepared in this example are a few templates. Let's take a look at them. So we have one pier template. This is a very simple pier template, but we have pier template that is a bit more detailed prepared for later. But what we will do in this example, we will have the middle span a bit longer. That's why we will need higher girders. That's why we had made a vertical step here. And what we can also define with these new station types is that we can fix the height of this pier head of this element so it will remain at a constant height. We will see how this works a bit later when we will create our own template for the main girders. We have also one template for the pile caps with 8 piles, and here also the height of the pile cap is fixed. Then we have a more detailed pier, which will be used later in the project, and we will see how we can easily replace elements by using templates. What we can also do and prepare as a template is the abutment. So we have a very nice shaped abutment here, which can be then also easily placed and positioned on the final 3D element. But now I would suggest that we start modeling the bridge that we have seen on the image before. And for this, I will start as mentioned in the theoretical part, I will use the drag and drop functionality. So I will just take first the pile cap, and here I will type in the name pile cap 01. Confirm it OK, and I can already see how this pile cap moves in the 3D window around. In the next step, I need to position it. And there I have many possibilities, but I will explain them just in a second. So let's take a look at the properties here. Okay, before I start my positioning process, I need to decide on which axis I would like to have it. And in this case, this will be the terrain axis because it's the foundation. So if I click on the terrain axis, I can see it starts moving along the axis. And also the station value is displayed. I will set the station 50 here. And now it is fixed on the station 50 on the terrain axis. And now the next few steps that I need to do are the vertical positioning. And here I need to first define the bottom position and then later on the top position. And for this, you can see in the properties, I have different options. Now I have set it to relative distance. And what does this mean? This means if I type in here minus 17 meters, for example, the bottom of the piles will always remain 17 meters below the terrain axis, and it doesn't matter how much the profile changes. But I could also set it to absolute height. And then this bottom of the piles will be at this absolute height position all the time, no matter how everything else changes. But for this example, I will keep it at relative distance and type in just here a value, let's say -17. Now the bottom position is fixed. And in the next step, I need to fix the top side of this pile cap. Here again, I will click on the terrain axis, set the station value of 50 meters, but now I will set for this offset 0 because I want the top of the pile cap to be directly on the terrain axis. That's why we go here with 0. This can also be changed later, and we will show this in a little bit. Okay, now let's continue building our first pier. I will take now the pier template element and position it on the pile cap. The difference in the definition process for this element will be that the first element was parametrically bound to one axis, but this one will be parametrically bound to two axes at the same time. We will see how this works. First of all, I need to select and define the bottom position. So let's select the terrain axis here. I will say station 50. And I want to be directly on the pile cap. This is why the offset at the bottom will be 0. And now I need to define the top position, which I will select the road axis, station 50, and with an offset of -1.7 meters. One little adjustment that I need to do here, because my bridge will go into this direction, and here I will have the larger span, I need to turn it by 180 degrees. So I can do this very simple by just clicking on the object, going to the properties, and set the angle rotation of 180 degrees. Okay, we have now the first pier element built. Now let's repeat this process for the second one. So I will again start off with the pile cap. Let's rename it to pile cap 2. And I will position this one at the station of 90. And let's say here -14. And again, the top side of the pile cap at station 90 and with an offset of 0. I will repeat the process one more time for the pier. This will be pier 2. I will keep the name and select the bottom position at the terrain axis at station 90, offset of 0, and go to the road axis now, also station of 90, but with -1.7. We are almost done with our substructure, but I just need to place the abutments. You have seen that I have created a template, and I will show you how easy it is to position them. So just drag and drop it inside. I will change the name to abutment start, for example, and position it only on the road axis. So here I will take the station value of 30 and the bottom, let's say almost 14 meters. And then the top position will be again parametrically bound to the road axis at station 30 and with an offset of 0.3 meters. Of course, I need to do the rotation again, but the same as is done with the pier, I set the angle to 180 degrees. Repeat the workflow one more time and create the abutment at the end. So rename it to abutment end, confirm it OK, and position it on the road axis at the station of 110. And again, the top value of 110 with an offset of 0.3 meters. Now our supports, our substructure is prepared and we can start placing girders. But we don't have them yet, so we need to create our template. And let's do this together. In the navigation tree, I will go to link girders and I will create a new link girder template. This I will name, let's say MG for main girder, but I will type here the value 1.1 because I will use two different types of templates. One will be a bit higher, one will be a bit smaller. But we can just copy them later and we will see how. Once I confirm the name, I will be directly in a separate modeling environment, an empty 3D space where I can model my template. But before we do this, I would like to quickly explain something about the properties, the stationing types, and the subdivision types that we can set here. From previous versions, you might already know global and local stations, but here we have two new types, relative and local end. We will see how this works in a little bit. For the subdivision type, I have also three different settings. One is begin and end. This means that the first station and the last station will be created. I can also click here on equidistant. This means that I create the first station, the last station, and the distance between the created stations in between will be equal. Or I can go with the free definition where I start by defining this virtual girder length and then define each station separately. And this is how we will do it so that we see the whole workflow. So I have set the subdivision to free and the type to local. First step, what I need to do, as I explained before, is I need to create a virtual axis. And this is the template length of the element. In this case, I will type in 10 meters, but this value doesn't matter later because we will determine the end geometry by defining this element between two 3D points. So let's type in just 10 meters. We see no element has been created yet, but the axis was created. This horizontal axis in a yellow color. This represents this virtual length. This can also be changed later. So I will start positioning now the cross section. So let's start at the station 0. I will confirm it OK. Then I will have, let's think about how I'm going to build this one. So I would like to have a constant geometry at the beginning and at the end. And by this I will have to use local and local end stations. So I will have a certain geometry up to 2 meters from the beginning and up to 2 meters from the ending. Let's see how we do this. So the first station will be at 2 meters. This is a point of interest for me. Here, I just need one element as well. We go for the subdivision type of total and type in 1. The next change will happen at 2.5. So go with total and again with 1. Here in the middle, I will have a few stations which do not govern the geometry of the girder. That's why they can move, let's say, respectively to the finalized length of the girder. That's why I will set here 5 or 6 elements. So I will set now the next station at minus 2.5, go with total, and let's say 6. Now we just need 2 more stations. One will be at 2 meters, a total of 1, and the last one at the end. Okay. Nothing special yet. We have created a few stations, but now let's go a bit deeper and see how all the new functionalities work together. So if I take a look at the stationing first, I will see I'm using different types of stations. I said that the first 2.5 meters are of interest to me because the geometry will be here constant. And also the last 2.5 meters, which are here because of the local end stations displayed in a negative value. This in the middle do not govern the geometry. That's why I will set them to variable or relative. And they will move respectively to the final length of the girder. In the next step, I will go to the variations. And here, I'm using the same approach as you have been using by the cross-section definition to apply variables. It's the same here because this happens on the cross-section level. So nothing has changed here. So for the height of this girder, I will first go with 1.1 meters, apply the expression to subsequent stations, and we will get this height. For the thickness, we will create a table, but I will come to this in just a little bit. Before we do this, I would just like to apply the material. I have already pre-imported some material inside, so assign material concrete and apply to subsequent stations. So this means that all resulting elements from this template will have this material representation. But let's go back to the variations and let's think about what we're going to do about the thickness. Because we are using different station types and we have seen that the local end stations have a negative value and the local ones have a positive one, we need to think about how we are going to build our variation table so that we can use only one table for the whole variation. So let's go and create a table now. I will go to variations, create a new table. I will just go mg thickness. And as we know, we build tables from the negative value up. So from the lowest one to the highest one. And I know that points of interest are minus 2.5 and minus 2. These are from the local end stations. And then the next one are at 2 and 2.5. I will have the girder. Let's say the girder will be at the beginning, at the end, a bit thicker. And in the middle, it will get thinner. And here I will set So for these values, 8 centimeters, here we'll go with 30 and 30, and here 0.08 again. But now let's see how we apply this variation table to two different types of stations. We begin the same as we did it always. We can drag and drop the table inside, but now a new window comes up. And this window asks us which station types are we going to use. And I will just start with local. And I see this geometry changes here. And these are the first 4 points of interest to me. I just need the last for one, so that's why I can delete everything that's in the middle, like this. But just one more slight change that we need to do. We see that we have, in the expression, we have this $sign and SL, which means local station, but at the end, we need to set it to local end stations. And this is done by replacing the L with the letter E. But do not worry, everything of this is explained in our F1 help. Now, let's apply this, recalculate, and take a look at the girder. And we see that we have now a nice changeable geometry, and we will see how this is applied in the 3D model. I've mentioned before that we will copy this one because we will need it twice, but with a different height. So let's copy this girder. Let's copy this template. I will just rename it in 1.85. But if I want to copy the variations with it, so I don't need to redefine them, I just click on variations and copy it. One last adjustment that I need to do is change the height here to 1.85. Like this. Recalculate, and we have a higher girder now. Now we can start positioning this fresh defined template element. So in the first span, I will use the smaller ones. So for the first one, I can just drag and drop inside, and I will change the name here to 1 - 1. So that means span 1 and element 1. And I will start the positioning process like this. Now I will use the multiple copy functionality like this. And here I want it to continue counting just for span 1, girder 2, girder 3, girder 4, and so on. So now I can just keep clicking on the reference point, and we see that the end and the beginning of the girder remains constant. And you can see that just in a matter of seconds, you can position so many elements. So here, just in a few seconds, I have positioned 7 elements, and my first span is done. Now we will start the positioning process here for the middle span, like this, and I will take the higher girder. So let's drop it inside, and this will be with 2 - 1, so span 2, girder 1. And we can see it how it fits here. Again, I will repeat the multiple copy functionality like this, so that we can complete this one easy and precise. So maybe just so that we see a bit better like this, and position the elements. Okay. Just more free to go. And we have finished our second span. Okay, I will repeat the process one more time for the last span. And for this, I don't need to place the girder one more time, but I can just use the one that is already existing and use the multiple copy functionality on one of the girders from the first span. So go multiple copy and start here with 3, like this. And you can see that in a matter of seconds, we have just placed almost 21. We are almost done, so it's almost 21 girders. But the key thing here is that these girders are positioned parametrically. What does this mean? I will show in a second. So for example, let's say that we want to move the position of the abutment. We will see how all the lengths of the girders in this affected span will automatically adjust. But before we do this, I would just like to place, for example, here in the middle, a diaphragm. And for this, I have also prepared a template for it, and we will see how easily it is placed. So just drag and drop it inside, and select this reference point, and just the one at the end. Like this. Okay, now let's say I want to apply some changes to the bridge, as I've mentioned previous. Now I want to move the abutment at the start. So for this, I will select the abutment start, and I will change the position to 25, or let's say to 20, so that it will be a bit more obvious. 20, like this, and we see how these girders have been stretched here. Very nice, easy, and precise. Okay, the next step, what I would like to show is, if you remember, we have some kind of more detailed piers, and I would like to exchange its templates. But do I need to remodel the bridge? No, I don't need to. I will just select the pier 1. So this is the first one, and I will select a different template. So the reference template will be pier detailed. For the second pier, pier detailed, and for the pile cap, I will say the detailed one, and also for the second one, the pile cap detailed. After a short recalculation, we will see that the girders remained at the same position, at the correct position, but we have now the more detailed piers. Also, another change that I can apply here is that I can change, for example, the vertical position of the second pier and of the pile cap. So let's go to pier number 2, it's this one, and I will set, for example, its bottom position to be 5 meters above the terrain axis. And of course, I also need to do it with the pile cap, also here at 5. And we have now this position 5 meters above the terrain axis. Okay, the next step is the road structure. And for this, we will use the deck element that we will find at the bottom of our organizational project tree. You don't need to do this, but I will create a master deck. So just to show you how this works. So a master deck is a deck created also in a separate modeling environment. For this, you can see I have this empty space now with both axes, and here I can define my road structure, or let's say my deck structure. I will select the axis, and I will choose the appropriate cross section, which is road, and I will just drag it, or by this I mean extrude it through the whole length, like this. 5, okay, and now I will just assign the material, and then I will position it on the final 3D element. Okay, back to the 3D model. I can now drag and drop this deck inside and position it on the bridge. Here, it's now positioned through the whole length of the axis, or how it has been defined in the master deck. But I can define where it's going to be cut. And for this, I will here set the cut a bit earlier. So just to show you later, that also the haunch is parametric. So let's say at 15 at 0, and then the second one at 110 and 0. Okay. Now we are almost at the last step, and we are going to model the haunch. And for this, I'm going to hide this abutment. And for this, I'm going to use our visual tools, selecting it, and add to hidden objects, and select. Okay. Now we can start modeling the haunch. For this, I will turn off the full 3D Boolean calculation. I will be still able to see the finished geometry, but the calculation and the definition procedure will be faster because not the whole bridge needs to be calculated. So select this, go to the 3D modeling, and select the Booleans. And I just do this with 2 clicks. So I select the deck, and then I select the assigned cross-section. And we see that the haunch geometry has been formed. Go again, Booleans, here, select the correct one. And it's the second one, and we see how this void or this gap is now filled. So this one, and just more 4 to go, like this. Okay, 3 more to go, like this. And we are almost done with the first span in just a matter of seconds. So this one, and just 1 more to go, and the haunch is completed. So last one. This one. Now I can go back to the calculation tab and turn on full 3D Boolean calculation, recalculate, and we will also see the material textures assigned again. Looks nice. Okay, if I turn back on the abutment, now what I can do to show you that also the haunch is parametric, I will move this abutment again to the end position of the deck. So this has been the abutment at the start, and I will move it to the station 15. So we will see that also the haunch adjusted. Recalculate. So we can implement changes here very quickly. And now, before I do the last change, I would just like to emphasize here the importance of this parametric approach. For example, once we have created this bridge, it is very easy to change spans, to add additional objects, or let's say to reuse this bridge for another project. Because you can save all the elements as templates, you can then just import them into your new project and just create a similar bridge, let's say in a matter of minutes instead of hours. So this is the real benefit here of this whole modular modeling approach. And now let's do the final change. I will change the axis. For this, I will go to the axis plan again, like this, and I will turn the axis from minus 250 radius to 300, for example. I'll go back to the 3D model, nothing has changed because I need to recalculate and do the recalculation procedure. And now that this recalculation is done, we have a whole new alignment. We could also just change spans, maybe assign different cross sections to our templates, and we will have a whole nother bridge in a matter of minutes. With this, I'm concluding my live demonstration. And for the end of the webinar, I would like to show you some of the videos that have been provided to us by our colleagues. The first example is an example of a precast girder bridge. You will see the whole workflow from the 3D modeling, parametric modeling process in Allplan Bridge to the designing and drawing production in Allplan Engineering. This example was created by Massimo Bellazari, who's the product manager for Allplan Italia. So thank you, Massimo. And let's take a look at the video. So we can see that the modeling process is similar to what we have done in the live demonstration. All the elements are placed between 3D reference points that have been defined on the substructure. Again, different types of variation tables can be assigned, so this will all be parametrically displayed through the whole bridge. And this is a nice example because we go from a 4 girder span to a 3 girder span just with a few simple clicks. Also, other parameters like height of the pier can be assigned, and also other objects can be placed here. So let's take a look what happens if we change this expression here. We have adjusted the height of this pier. What we can also do here, we can create bearings as templates. But this is not the only way that bearings can be placed, because we also have the functionality to place Python parts. And Python parts are parametrical objects that can be also visualized and positioned in Allplan Bridge with different parameters that can be changed throughout the project. But in this case, we see the assigning of bearings with the help of templates. So we see the finished model now that has been already exported to Allplan Engineering, and also the terrain model is present so that we'll see how it looks there. In Allplan Engineering, we can also visualize the construction sequence that has been defined in Allplan Bridge. Because in Allplan Bridge, as we have mentioned in the theoretical part, we can also do the construction sequence. And the elements are exported according to this construction sequence. Now we just go step by step by highlighting the elements so that we see how the bridge is going to be built with all the fine details that can be modeled in Allplan Engineering and with all till the road structure at the end. Looks nice. So once the model is fully imported and once the model is fully detailed in Allplan Engineering, we can go to the drawing production. We can with ease generate sections along the bridge or sections perpendicular to the axis, as we see here. So really, Really simple and accurate, and we see that the detail that is provided by creating these sections, and these models do not need any adjustments, that they look construction site ready. So, okay, so this is the finished product. Thank you again to our colleague Massimo. And the next example that I would like to show you is also a user example that was created by our colleagues from Cable Tech in Korea. It's also a precast girder bridge, and for this I will share a video with you. Thank you again to our colleagues at Cable Tech Korea for providing this video for us. With this, I'm concluding my webinar, and I would like you to ask questions that haven't been answered during the webinar at this email address. So you can get in touch with us at info.infra@allplan.com or at support.infra@allplan.com. At this point, I would also like to invite you to our Infrastructure Day, which will be on the 4th of May, where we will show the whole process from the beginning of the Precast Girder bridge up to automatic reinforcement and automatic drawing production. Thank you all for being today with me. Hope you have learned something new, and I wish you a nice rest of the day. Goodbye.